Welcome back to an exciting adventure in 441A, 541A. Homework number 2 is due in a week on Wednesday, next Wednesday, and our exam is a week from Friday. It's coming up quite quickly. Lab number 1, you will want to understand what is going on in lab number 1, but it's not due until after exam number 1. But you should be able to get your team member assignments from D2L and also the system associated with your team number for executing the lab. And that particular system, the spring number and the number of masses, will follow you throughout the semester in the subsequent lab. So you'll be using the same system throughout the semester. What we want to do today is work through a vector linearization example. We talked about it in general, this concept of linearization. Let's see if we can start to maybe visualize what's happening with linearization. And then we will jump into the subject area of system identification. That's really what lab number 1 is doing, is system identification, but it's doing it with a second order system. We will start the process by looking at a first order system and trying to identify the system behavior, a transfer function, by applying a constant input to a first order system. Linearization is what we were talking about not yesterday, the day before, whenever we last met. And that dealt with x prime equal to f. F was a function of x and u. X can be a vector, u can be a vector, and f is a nonlinear combination of x's and u's, or different components in x's and u's. And we went over what that means last time in terms of what does it mean to be nonlinear. We could have a product of terms, we could have a nonlinear operator on some of those components in the x and u vector. In linearization, what we're doing is we're trying to identify an operating condition about which we can linearize. Typically, that operating condition might be a point. If you were thinking about balancing a pencil on your hand, that could be a system, and the equilibrium is when it's in the upright position. And your goal is to maintain that, or what are the dynamic behaviors or behavior of that system around that upright, stable, well, it's not really a stable condition, but that upright equilibrium condition. You can also think about a satellite orbiting the Earth. That's not in a point, that's not at a point, it's on a path. And now if somebody bumps it off of that orbit just slightly, how does it dynamically respond to that delta x away from the orbit? Does it come back to the orbit naturally? Do you have to control it to get back to the orbit? Is it unstable? If you bumped it away from that orbit and didn't do anything, would it just gradually leave or very quickly leave the orbit? That's what we're trying to understand, is how does the system behave around the operating condition? How does the linear system behave? And that's what we're trying to establish, is a linear model of this nonlinear system around the operating condition. And the operating condition that we are using is we're using a subscript 0 on the state vector x and the input vector u. And we're saying that that operating condition, this orbit around the planet, means that it's satisfying that nonlinear differential equation, the x naught u naught. Or that's the equilibrium point about which we are linearizing. And we want to work through that for a second order system. Here is maybe a visual of what I'm talking about. These highlighted lines through the origin are actually eigenvectors, and the point that you are at away from the equilibrium condition. The equilibrium condition in this example is the origin. x1 is 0 and x sub 2 is 0. But now if you moved away from the origin, imagine you're now a little bit away on one of those green curves. This is showing you how you would naturally come back to that equilibrium condition, depending on where you are located in the phase plane being the x1, x2 plane. And in this case, since all of these trajectories are pointed towards the equilibrium condition, this is a stable equilibrium point. And we want to know, if we do linearize a system about the origin in this case, is the linear system naturally going to be stable, unstable? If it's unstable, that's the reason why we might want to control it. That's why we're taking this class, is to learn how to stabilize unstable systems, how to make a system more robust to uncertainties, how to make it track certain trajectories that we might want it to follow. And this now is our second order example that we want to work through. If it's a second order example, then we have an x1 prime and an x2 prime, and we have two right-hand sides, or two components on the right-hand side. An f1 nonlinear expression, possibly, and an f2 possibly nonlinear expression. It doesn't require both f1 and f2 to be nonlinear for the whole thing to be nonlinear. We just need to have one nonlinearity somewhere in f1 and f2. f1 might be a linear combination of x1, x2, and u. f2 might be where the nonlinearity sneaks in. But all it takes is one. Just like stability, it only takes one unstable pole to cause the whole system to be unstable. If this is the setup, then we talked last time about a Taylor series expansion, where we now are going to be performing this Taylor series expansion about the nominal operating condition. And the nominal operating condition is x sub 0 prime is equal to f sub 0. And here I've simply illustrated that for a second order example. And what I've underlined in green, or overbarred in green, that's what we are assuming is true. We're assuming that the nominal operating condition is satisfied. So the x0 prime equals f sub 0 prime. And that's, if we have 6 equal to 6, we can basically cancel that out and just be left with this delta of x prime on the left equaling, and there's more down below. All I've shown so far is the partial of these f's with respect to the x vector. There's also a partial of f with respect to the input vector, which is there. All of that now combines to give us our linearized behavior of this nonlinear system about an operating condition, where what I've highlighted in the dashed red is our system matrix A and our input matrix B, and that's after we evaluate, after we've performed these partial differentials on the f with respect to x's and u's. We evaluate those for x1 naught, x2 naught, and u naught. And that will give us a constant A matrix and a constant B matrix. I think the next screen is really just showing the result of what happens when we cancel the x0 prime equal to f sub 0, which is what we're assuming is true around the operating condition. This is exactly what I had before. It's just we canceled two equivalent pieces on either side of the equality sign. So that's a lot of partials to be writing down, but let's go through an example and put this maybe more solidly or firmly into our head by looking at a specific example where we now have x double prime is equal to some function, nonlinear function of x, x prime, and u. So here's the example that I want to play with. Let's assume that the second derivative of x is equal to 4x plus 6x x prime minus x prime squared. This is still on the right-hand side, plus u x prime plus 5u. All of that is our nonlinear right-hand side that I've labeled G up above. Do we have any nonlinearities in G? Or is G nonlinear? Yeah, we have a lot of nonlinearities in this one. We have x times x prime, we have x prime squared, we have u times x prime. Those are all three nonlinearities, and any one of those by itself would cause the whole system to be nonlinear. So now what do we do? Well, the first thing that we want to do is maybe, does this look at all like that? First derivative equal to a right-hand side. Maybe not so much, huh? So now we need to convert this into a coupled system of first-order differential equations. What's the order of this differential equation? If it's second order, why is it second order? Because I have a squared on the right-hand side? We're differentiating x twice. So we have a second order nonlinear differential equation, which means that we probably are looking for two first-order differential equations that will be coupled. To establish that, let's go ahead and define some new variables. Let's let z1 be x. And how many components in the z vector do I need? Do I need a z1, a z2, a z3? How many z subs do I need? Why do I need 2? So you're saying, well, I kind of gave it away by putting the and sign there, didn't I? I should have done this. I should have said, how many z's do you need? I gave you the answer if you were awake. Wake up call, lights on, time to rise and shine. So z sub 2 is what? Let's let that be x prime. And now this will allow us, because what do we need? We need to keep going with the components in z until, if we differentiate that component once, will we finally get to the highest powered derivative in our nonlinear equation. And we have an x double prime. If I differentiate z sub 2 once, I will then get the x double prime that I need. So I can stop with the components in z at this point. So now what I want to do, I want to let z1 equal x and z2 equal x prime. And now I want to rewrite equation, that second order differential equation, as 2 first order coupled nonlinear differential equations. I now want to try to find right-hand sides for a z1 prime and a z2 prime in terms of z1, z2, and u. U is a scalar input. Let me start then by saying, okay, what is z1 prime? If I differentiate z1 once, well, I've defined z1 to be x. That's the same then as x prime. And now I want to see, do I have an equation for x prime, or can I rewrite x prime in terms of z1, z2, and u? What is x prime? I defined that to be z2, so now I have z1 prime is equal to z2. That's actually my first right-hand side. F sub 1 as a function of z1, z2, and u. It's only a function of z2. Is it a linear function of z1, z2, and u, or nonlinear? It's linear, isn't it? So that's not incorporating any of the nonlinearities, but that's okay. We'll probably have some nonlinearity on the right-hand side in f sub 2. Z sub 2 prime is x double prime, and that's our messy right-hand side, isn't it? Now we just rewrite that right-hand side in red in terms of z1 and z2, how I've defined them. So I now have a 4 times z sub 1 plus a 6 z1, z2 minus a z2 quantity squared plus u z2 plus 5u. Is that right? So let me write that down. I have a 4 z1 plus a 6 z1 z2 minus a z2 squared plus a u z2 plus a 5u. And all of that is the right-hand side associated with the second equation. So that's f sub 2 of z1, z2, and u. Just establishing notation. And now I have what I need. I have z1 prime equaling an f1, and I have a z2 prime equaling an f sub 2. I'm now in a position to start taking the partials of these f's with respect to z1, z2, and u to try to do the linearization. Let me do the first one. I'm going to then end up with a delta of z1 prime equaling partial of f1 with respect to z1 evaluated at z1 equal to its nominal value. Let me put a 0 in the subscript of z1, so I have z1, 0, z2 at its nominal value, and u at its nominal value. And I haven't even found those yet, have I? I don't think I've said what those are yet. But now I need to multiply that partial by the small variation about what? I'm taking the partial with respect to z1. This is now z1 minus z1, 0, or all of this together, this little piece, is actually just delta z1. I need to keep going. I need to take the partial of f1 with respect to z2 and the partial of f1 with respect to u, and then I'll be finished with this first equation, linearized. So I have the partial of f1 with respect to z sub 2 evaluated at, I'm just going to say z1 naught, z2 naught, u naught, times, what am I multiplying this by? The small variation around what component? z1, z2, or u? I have 3, don't I? But this was the partial of f1 with respect to z2. This is now z2 minus z2, 0, or this is now the small variation of that second component of our z vector. One more piece to this puzzle on the right-hand side, and that is partial of f1 with respect to u. Again, once I've evaluated or found the partials, I replace all of the z1, z2s, and u's with the knotted versions or the operating condition. And this is the small variation of u about u naught. Is it clear where this came from or how we found this? Now we should be able to automatically write down the second one. It's the same structurally, it just involves f sub 2. The second one then is going to be delta z sub 2 prime is equal to partial of f2 with respect to z1 times z1 minus z1 naught, and that is just delta z1 plus partial of f2 with respect to z2 and finally the partial of f2 with respect to u. Now we could go home with our toys if we were finished. Are we finished? Do we have any numbers for these partials yet? We're looking to find numbers for those, aren't we? Coefficients for partial of f with respect to these z's evaluated at the operating points or operating condition. So we now need to find an equilibrium condition around which we are going to linearize. or plug in those values to these partials. What is an equilibrium condition? I'm just going to say that many times this equilibrium condition is actually an equilibrium point, just like this pencil in your hand. That's a point with which you're balancing. It's not the orbit of a satellite. That would be an equilibrium condition. It's going, and you're now linearizing about that. Here it would just be a point or a condition. Many times it is an operating point this equilibrium condition, and we are looking for values of, in this case, Z1, Z2, and U when the time rate of change of Z1 is 0. Now we're looking at a point. So Z1 dot is at some equilibrium condition. We want Z2 prime to be 0. If that's the left-hand side, what does that imply is happening to the right-hand side in our, here we're saying Z naught prime is equal to F of Z naught U naught. This is the equilibrium condition. If now the column of Z's on the left are equal to 0, what does that imply happens on the coordinates or elements in the F vector? If we have an equal sign between them. So the F's have to equal 0, don't they? So now Z1 prime being 0 says that F1 of Z1, Z2, and U needs to be 0, and F sub 2, since Z2 prime is 0, at the operating condition. So this is now all of these subscripts at the nominal value. And we have those equations. Here's F1, that's Z2, and F2 is this mess. We now want to see if we can find values of Z1, Z2, and U that will cause these F's to equal 0. So if we're forcing F sub 1 to be 0, what does that imply? That means Z sub 2 at its operating condition is 0. So now based on this, F sub 1 of Z1 0, Z2 0, U 0 is F sub 2 0, and we're wanting that to be 0. Now we have one of our nominal values of our elements determined. Z2 0 is 0. If this is 0, if F sub 2 is 0, let's now go back to that involved equation. There's F sub 2, and if we put Z sub 2 equal to 0 in this, do you see that that annihilates that term? If Z2 is 0, Z2 is 0 gets rid of that one. Z2 of 0 gets rid of that one. Now we need 4Z1 plus 5U to equal 0. And we could make that happen many different ways. Let's just do it at a easy way. Let's set z1 to 0, and then what's that force u1 or u to be? 0. So that's now an operating condition or an operating point that we are linearizing about. Is it clear where that is coming from? F1 forced z2 of 0 to be 0. Then the highlights say, well, if z2 sub 0 is 0, we've already eliminated 3 of the terms. Now we just need those last 2 to combine in such a way to give us 0. And we said, well, a trivial way to do that is make z1 0 and then u is 0. So now everything is 0 that we're linearizing about in this nonlinear equation. The fact then that F2 is 0 is going to then imply on our judgment that z1 of 0 is 0 and, or on our decision, u sub 0 is 0. Those are now what we will use to evaluate after we've performed the partial derivatives on all of these f's. One of the first partials is partial of f1 with respect to z1. And what was f1? That was z sub 2, was it not? And what's the partial of z2 with respect to z sub 1? Is z1 involved in z sub 2? What's z sub 2 look like relative to z1? It looks like a constant, does it not? So this is now 0. So the partial of f sub 1 with respect to z1 is the partial of z2 with respect to z1. Is there any functionality in z2? Is it a function of z1 in any way that we can differentiate with respect to z1? No, it's 0. What about partial of f1 with respect to z sub 2? F sub 1 was z sub 2. What's the partial of z2 with respect to z2? That's 1. And now we have one more partial associated with our f sub 1. We have the partial of f1 with respect to u. What happens when we perform that partial? Is u2 anywhere, or is u anywhere in z sub 2? So now we have half of our partial stuff done, and we didn't even have to evaluate these at a nominal condition because there were no z1, z2, or u appearing after we performed the partial. Let's look now at f2. Suppose we now take partial of f2 with respect to z1. So if we go back to our f1 equation, which is right here, and differentiate that with respect to z1, what are we going to end up with? If you differentiate f sub 2 with respect to z1, the partial derivative, now you're looking at all of these terms that have a z1, and for z1, differentiated with respect to z1. Is that 13? No, it's 4, isn't it? So it's 4. Do we have anything else? A 6 z sub 2. Is it clear where that came from? What's the partial of f sub 2 with respect to z sub 2? Now we go back and look at f sub 2, find the terms that involve z sub 2, and perform the partial differentiation. 6z1 minus 2z2 plus u. Whatever we just said. 6z1 minus 2z sub 2 plus u. And finally, partial of f2 with respect to u. And u was a couple places in there. It was times z2, and it was 5u, so now we have z2 plus 5. Do you see what happens when we evaluate these at the equilibrium condition? If we have z's and u's, our z's and u's we said are 0 in this particular example. So now the partial of f2 with respect to z1, that just becomes 4. The partial of f2 with respect to z sub 2 becomes 0. Partial of f2 with respect to u, 5. So now if we plug all of those in, we now have our linearized dynamics around that nominal point. 0, 1, 4, 0. This is now our system matrix A, and here is our input matrix B. And now we can start asking ourselves some questions about the dynamic behavior of this linearized system around the operating condition. We're operating around the origin. How is this system going to naturally behave close to that 0? We're not going to go very far away. We're just interested in the dynamics of these deltas. Delta Z1, delta Z2, and delta U. We only want to venture a little bit away. If we get far enough away, our linearization is not valid. Is that clear? So we're trying to isolate on a small region around the operating point in this case. And now we want to know, how does this system naturally behave? Is it stable? Is it unstable? Is it marginally stable? What are the natural dynamics of this linearized system? Or what governs the natural behavior of this system? Where do you get the underlying dynamical behavior of a linear system? What are you looking for or at? If I gave you a transfer function and I said, how is this system going to behave? What would you give me in reply if I gave you a transfer function g of s? The poles. You would be looking at the roots of the denominator polynomial. Now, if this is not in the frequency domain, the poles are in the frequency domain. This is a time domain system, but we could put it into the frequency domain. We don't need to. What can we associate with the poles of the transfer function in the time domain expression? The eigenvalues of that A matrix. The eigenvalues of the system matrix give us information about the natural behavior of the system. And if it's not like we want, then we figure out, how do we inject U input to change those dynamical behaviors or that dynamics. Let's now look at the eigenvalues of A. And you were wondering why you took 310, huh? You had eigenvalues in that class, did you not? ECE 310, and you've had it in all of your math linear algebra classes if you've taken those. The eigenvalues of A are now the determinant of, and I'm just going to call those eigenvalues lambdas, lambda I minus A. There's lambda I. I subtract the A matrix from that and compute the determinant. That's what the straight vertical bars indicate. And the determinant of a 2 by 2, you don't even need MATLAB for that, I hope. It's the product of the diagonal minus the product of the off diagonal. We have lambda squared minus 1 times minus 4, or minus 4. And if we set that equal to 0, the values of lambda will be the eigenvalues. Lambda squared is equal to 4. We have 2 lambdas. It was a second order system, a 2 by 2 system matrix. We would hope we get 2 eigenvalues, a lambda 1 and a lambda 2. And a lambda 1 when it's squared needs to give us 4, and a lambda 2 when it's squared needs to give us 4. What are my eigenvalues? Are you happy with this system's behavior around that origin operating condition? Now you don't even have to remember plus or minus. You know you've got one of each. This is unstable, isn't it? Which one would be the stable pole eigenvalue? If I plotted those eigenvalues in the S-plane, well, now I'm going to go real S, so now lambdas become S magically, but I hope you understand what I'm trying to say. Where are those eigenvalues going to live? One's over here at plus 2, and one's over here at minus 2. What modes do those give rise to in the time domain? If I went up and just kicked this system, this nonlinear system, just ever so slightly to nudge it away from the equilibrium, the 0, how would it behave? Well, this is how it's going to behave based on these poles. But these poles provide information about the modes of this response. And what does that mean? These give us the exponent in our E terms. We now have, due to this, what color am I on? What color do you want it to be? I'm not going to get too creative. This one now leads to an e to the plus 2t mode. What does this one lead to? An e to the minus 2t. So which one is well behaved in terms of giving us a bounded response? The one on the left of the imaginary axis. The eigenvalues in the left half plane are the good ones. They're stable. The ones on the right-hand side, that's going to go unbounded, is it not, with time? That's the one that's giving us the problem. And we only need one of those. If we had 100 poles and only one was in the right half plane, better watch what I'm doing. I don't want to throw microphones around today. That cost me. But none of you heard that YouTube lecture, did you not? Yeah, I didn't post it. It's private, okay? But I did create 2 segments from Monday's lecture. So now if you go back, you'll see it packaged in 2 different pieces. All right, any questions on linearization? Do you see which one? This is now the unstable mode, and this one is the stable mode. And it all is what? Well, we no longer have any information to worry about. Our screen is blank. I hope there that I just had a little bit of a mislocation of the finger. What do we want to do now? Our next activity is actually going to be system identification. Is it clear what we want to do with system identification? If I ask you to draw a picture in the time domain of a first order system response, could you do that? If I said, imagine a first order system, and now we apply a constant input to that first order system, what's its response look like? Can you draw that? That's not a rhetorical question. That's a question that demands action. Suppose we label that as y of t. This is the output response of a first order system that I've now applied a constant input to. What does that look like? And what if that catches you off guard? What could you do if somebody says, first order system? Oh, what's he talking about? Well, most of you are electrical engineers, electrical and computer engineers, right? What could you build quickly on paper? You could even go over to the stockroom and pull some parts out of the window and build it. How could you build a first order system? What's something that maybe immediately comes to mind for a first order system? A couple of resistors and a voltage supply? No. We need some kind of energy storage device, don't we? We need something to give us a first order behavior. What if I gave you a capacitor and a resistor? Could you build me a low pass filter? Sure. And then you need to follow that up with building a low-pass filter, correct? And you could tell me the bandwidth of that low-pass filter based on the resistor value and the capacitor value. But now if I gave you an RC filter and said, what's its response due to a constant input? If you now applied 4 volts to this RC filter, what would its output response look like? If you didn't have an answer already, do you have one now? Okay, this is before you exit class and go through the student union at the career fair, you have to be bright and know how to respond on these kinds of questions. This is an interview question, is it not? Sketch a first order system, or give me a low pass filter. Analyze that low pass filter. What's its step response? Did it look something like that? That's a first order system response. There's no wiggle about it. It just exponentially goes to its final value. What we want to do is now say, oh, you have a black box. I'm going to apply a constant input to that black box, and then I'm going to tell you what's inside that black box in terms of its transfer function. That's what we're doing with system identification. And how we will do it for a first order system is we will just figure out where it eventually gets to, what's its final value, and how fast did it get there. Those are the only two pieces of information we really need to model a first order system, is where are you going and how quick did you get there. That's all we need to identify a first order transfer function. We'll pick up at that point next time.